All right, everybody, we are back. This is day 2 of rotation notes, and we're going to begin with a warm-up problem. All right, so day 2, rotation. What I would ask that you do is take a look here, maybe freeze frame, give it a try, and then I will go over this one in a little bit. So again, let's pause, take a look at the question, give it a try in your workbook or your notebook, and then I'll be back. So I'll be back in a moment once you restart the video. Okay, so we are back. Let's go over this one. All right, so this seems a little different. Long thin rod with moment of inertia. What the heck is that? I don't know, we haven't done it yet, but I'll just jot it down just in case. Kilograms times meters squared. Blah, blah, blah. Rotates from rest. Okay, rotates from rest means that my initial... Sorry, let me scooch this over. I zoomed way in so that we'd be able to see the multiple choice, but my writing's kind of big, so I may have to zoom back out again. In fact, let's see if I can do that. Oh, I'm so technologically good at this stuff. Oh, you should be so proud of me. My kids would be proud of me, my children. Anyway, so we rotate from rest, so that means our initial velocity is 0, and we are accelerating. Our final angular velocity is 4 pi rads per second, and it rotates through 2 revolutions. And if you're wondering what that is, that's theta. Okay, now granted, we're going to change that into radians because as you look at your choices here, everything's in radians. So a reminder that 1 revolution is 2 pi radians. Therefore, if you have 2 revolutions, you're going to have 4 pi radians. So that's going to be theta. Okay, so we're trying to find average angular acceleration. So if I think back to kinematics, the main thing I do not know here is my time. I know how far it goes, and it's 4 pi radians. I know the initial velocity, I know the final velocity. That inertia, you don't need it yet. It's kind of a distractor. So what I'm looking at really, and you'll notice how I do this, like I said, I don't really memorize all of the kinematic formulas and memorize them in rotational form. I tend to keep them in translational form in my head and then substitute as necessary. So that way I only have to know one. I clear up a little space up in my brain when I do that. Okay, so that's really what that one's going to look like. I'm solving for alpha. I'm solving for angular acceleration here. My initial velocity is 0, so it's going to be omega final squared divided by 2 theta. And once I do my substituting, this actually isn't so terrible, right? So I'm going to do 4 pi, I'm going to square it, I'm going to divide it by 2 on 4 pi radians as well. So, oh, I'm almost out of the screen here. Let's be careful. So I've got 16 pi squared over 8 pi, and I can do a little canceling. And let's see, oh, it's choice E, 2 pi radians per second squared. All right, so hopefully everybody got that one. And the second question here is identical. I was trying to make it easier when I Xerox them. I could just cut them in half, but we don't really need to do that. Okay, so now that you're warmed up with a little bit of review from kinematics, we're going to look at material for rotation day 2. And the focus here, I've got a few specific topics to cover. And then again, I want you to practice with your WebAssign. The main focus, my first focus for today is to look at the relationship between, let me write this down before I forget what I'm doing here. Okay, so the main thing I want to do, I have 3 key things. I want to focus on the relationship between rotational motion and translational motion, how you convert back and forth, introduce the idea of rotational kinetic energy, and then a very brief moment of inertia introduction. Okay, so we will definitely do a lot more with moment of inertia later, but today we're just going to touch on it very, very quickly. Okay, so first of all, let's start with the relationship between translational motion and linear motion. Oh, I'm sorry, I said that wrong. And rotational motion. An object can be spinning and still moving in a straight line. You know, think about a boomerang. It's spinning, but it travels from point A to point B. It's got a linear component to it. And what you can do is you can take that rotational motion at any point in time and figure out the translational part. if you're talking about, oh, I'm moving with this angular velocity of such and such with a radius, how fast am I going? You can either leave it in angular format, or you can change it to translational format, to linear format, and we have a way to do that. It works really very well also with distance, theta versus and distance, and it works very, very well with angular velocity to linear velocity, or I'm sorry, I said that wrong. Whew, it's hard when I'm not like looking at a class. I'm looking at a bunch of blank seats in my classroom right now, trying to do this without making too much of a mess of it. So if I have angular acceleration, you can change it to linear acceleration very, very easily. So let's look at the change for angular velocity to linear velocity. And I am going to derive this for you, but you're not going to have to derive it every single time, and you're not going to have to derive all the other ones as well. But let's consider our circle again. Let's consider our radius, theta, and our arc length, just like before. And as you know, theta is the arc length over the radius, or you could actually write it this way. Okay, now, if I were to look at how fast I'm going in a linear fashion, I mean, keep in mind, depending upon how far out your radius is, if you take any point along that radius and you say, how fast is it going with angular velocity, it would be identical. It doesn't matter where you are, right? You're still covering the same angle in the same period of time. Right? But if you're talking about linear velocity or translational velocity, how far away you are from the center of the circle does matter, because your arc is going to be bigger. Therefore, you're going to travel further in the same amount of time. Therefore, you're going to go faster the further out you are. And I was a little muddled about this in day one. I apologize, but the further out you are, or the longer the radius is, the faster you're going, not the slower. So, to be clear, all right? But if I want to figure out just linear velocity in general, and I want to look at it from an instantaneous standpoint, so I'm going to work with just calculus here a little bit. Nothing too scary. You don't have to close your eyes. It'll be fine. But I want the change in this arc length, right, over the change in time. That's what I'm looking at for a velocity here. Now, if I take this and I work with this as well in terms of a calculus perspective, right? What I could do is actually say, well, what I'm really doing here is I'm taking, all right, ds dt, this piece right here. My radius should be fairly constant, but I'm going to take my angle, I'm going to chop it up into smaller and smaller bits. Now look what I'm doing here. I'm getting ready to substitute. I don't know if you noticed that or not, right? So I have these two are exactly the same. So I can say V equals R d theta dt. It should look a little more like a D. All right, I'm just substituting 1 and 2. All right, they're equivalent to each other. Now, if I ask myself, well, what is this? That's my classic definition for angular velocity, isn't it? It's the change in theta with the change in time. So what I can simplify this to, and this is my overall piece here, is that I can take any angular velocity, multiply it by the radius, and I will have the linear velocity at that moment. Okay, so this formula, this relationship is critical. You need to know this formula. You do. It is going to save your cookies so many times, you're not even going to believe it. Now, also, we can use the same sort of relationship with acceleration. My linear acceleration is equal to my angular acceleration times the radius, using the same sort of logic, okay? And we don't really typically use that relationship much with distance, but that's really, essentially, it's that relationship right there. All right, I'm taking my change in theta times the radius, and it will tell me the linear arc length. So that's actually the first one. It's right there. We just don't use it quite as much. Okay, now we've got a couple of other things too. Because I have this relationship, that fantastic centripetal acceleration formula that we have used in the past for things that are moving in a circle, we can actually rewrite it in an angular form as well. if you put in your angular substitutions here and square it as if you have, like you do here, you could actually also just write it like this. So depending upon what you need, if you're dealing with centripetal acceleration, centripetal force, that may be helpful as well. It's not unsolvable if you have things that are in angular format. Okay, so with this in mind, and with these very, very important relationships now in our arsenal, let's move on and actually do something with them. We're going to look at the idea of rotational kinetic energy. That's really our next one here. I'm going to go to a brand new page to make life a little bit easier. All right, so energy and rotation. The cool thing is that most of what we know about energy is exactly the same. Makes it really, really simple. All right, so let's think about something, say, rolling down a hill. Before, we said, oh yeah, look at what kind of energy we have here. We have gravitational potential energy. And oh look, what kind of energy do we have here at the bottom? We have kinetic energy. But you know what? There is an energy associated with this turning around in a circle as it rolls down the hill. And we haven't accounted for it yet. I don't know if you remember, but back when we were doing the momentum lab, and I said, all right, guys, you need to figure out how fast the ball is going as it leaves the table. I was really specific with you. And some of you guys were like, oh, well, why can't I just do, potential energy at the top of the ramp, and I can do kinetic energy at the bottom of the ramp. And you know what? On the surface, that really seems like an awesome, awesome idea, except there's a whole piece of kinetic energy we have not even accounted for yet, and that is rotational kinetic energy. I don't mean the fact that it is moving in a straight line. I mean the fact that it's actually spinning as it rolls. It rolls. It doesn't slide. It doesn't skid. It actually rolls. And that's a whole other form of kinetic energy. So when we look at this from a conservation standpoint, if you are turning as you are moving down the hill, then you also have to consider, let me say it's going this way, of course, right? We're going to have two types of kinetic energy. You're going to have translational kinetic energy, and you're going to have rotational kinetic energy. And in order to be truly accurate in your energy conservation, you do need both. Okay? So, what in the wide world of sports is this one going to be? Well, you know what? We can take our lead from the translational formula. Okay? Regular kinetic energy, we say, is 1/2 mv squared. Okay. Well, what do we know about v squared? Well, we just did this whole, rotation thing, right? So we know that it's the same as angular velocity times the radius. Let's square that, and let's see where that leads us. Okay, so that technically is it. Now I'm going to move things around a little bit. I'm going to put the m and the r squared bit right there, and I'm going to put this out here. Now this is a crude representation of what we call moment of inertia. And we are going to, we'll take a look at that. We're going to say, assuming we have a system of particles, what we can do, we're going to rewrite this. We're going to say it is the sum of all of the masses times all of the radii squared. And I'm just going to use this little symbol of, here I'm going to use these little eyes, because it depends on how many particles that you have. Okay, this times omega squared. Now, this is what I call moment of inertia, and we're going to spend a lot more time on that in the future, and it's going to have a few more permutations that go along with it. This, of course, we should recognize as angular velocity, and the 1/2. So really, when I rewrite this, I'm going to put it up here because I've got a little bit better room, we say, okay, well, translational, 1/2 mv squared. Rotational, 1/2. Now I call this moment of inertia. The symbol for that is I, and omega squared. And what I'd like you to do is to take a look at what's going on here. All right, somehow, rotationally, moment of inertia corresponds to mass. And of course, angular velocity corresponds pretty easily to linear velocity. But what this is, and like I said, we're going to spend a lot more time on it later, but this is the rotational counterpart to mass. So we say mass has inertia, it doesn't want to change its velocity, doesn't want to change whatever kind of motion it has. This is a rotational inertia. It's a resistance to the change in rotation. So if it's already turning, it doesn't want to stop turning. If it is not turning at all, it's very resistant to start turning. So it goes right along with linear inertia, which is to get it changing its velocity in a linear format. But this one is going to be resistant to changing its rotational movement in whatever plane you're working with. Okay? This formula, I know I just wrote all over it, but this is another really important one to put in your arsenal. You're going to need this one, okay? This whole thing with the system of particles, meaning you're going to take the mass times the radius squared for every single particle. Systems of particles, rare. We don't deal with them all that much, but they occasionally come up. Often we're dealing with geometric objects or something that has what we would consider an infinite number of particles to it, and we have some geometric formulas that will help us with that. But more on that later. We're not going to worry about that right now. Right now we're going to see that we have another type of kinetic energy to go along when we deal with energy conservation, and we have this new term called moment of inertia that's all about not wanting to change the motion in a turning sense. So no way to, there's a resistance to that kind of change. All right, so you've got some homework. Again, WebAssign number 2, I want you to give that a try. And again, if there's something you can't solve, or if there's something about these notes that you can't, wrap your head around quite yet, please write it down. I'm going to be back on Monday, and I will start the class off with trying to answer those questions for you, make sure everybody is up to date, and then we're going to move on from there. All right, you guys, have a good one.